Normally, when I have you investigate one of Newton's laws of motion, I do the data collection part first, and then you kind of put together the understanding of the law. But for Newton's third law, I want to go backwards. I'm going to help you understand what Newton's third law says. I'm going to give you some examples, and then I'm going to give you some real-world examples. And by the time you get to those real-world examples, I want you to be able to pick out the different parts of Newton's third law and put them together in kind of in the way that the law is stated. So the information we're talking about is from a website called the Physics Classroom. And this is what the Physics Classroom has to say about Newton's third law. We know that a force is a push or a pull upon an object that results from its interaction with another object. Forces result from interactions. Then I want to go down here and talk about, according to Newton, whenever objects A and B interact with each other, they exert forces upon each other. For example, when you sit in a chair, your body exerts a downward force on the chair, and the chair exerts an upward force on your body. Notice, how many forces are there? 2 forces. There are 2 forces resulting from this interaction. The force on the chair and a force on your body. How many objects are there? 2, the chair and your body. These 2 forces are called action and reaction, and they're the subject of Newton's third law. Formally stated, Newton's third law says, for every action, there is an equal and opposite reaction. So to break that statement down a little bit, the statement means that in every interaction, there is a pair. Haha, forces come in pairs. Acting on the 2 interacting objects. 2 forces, 2 objects. The size of the forces on the first object equals the size of the force on the second object. The direction of the force on the first object is opposite the direction of the force on the second object. Forces always come in pairs. This is an equal and opposite action-reaction force pair. Can you imagine what would happen if, when you press down on the table, go ahead, do it now, press down on the table. When you push down on the table, what if there was not a force pushing back on your hand? Something to think about. A variety of action-reaction force pairs are evident in nature. Consider the propulsion, or the movement, of a fish through water. A fish uses its fins to push water backwards. But a push on the water will only serve to accelerate the water. It only makes the water move. Since forces result from natural interactions, the water must also be pushing the fish forward, propelling the fish through the water. The size of the force on the water equals the size of the force on the fish. The direction of the force on the water, which is backwards, is opposite the direction of the force on the fish, which is forward. For every action, there's an equal in size and opposite in direction reaction force. Action-reaction force pairs make it possible for a fish to swim. Now let's consider the motion of flying birds. A bird flies by use of its wings. The wings of a bird push air down. Since forces result from mutual interaction, the air must also be pushing the bird up. The size of the force on the air equals the size of the force on the bird. The direction of the force on the air, down, is opposite the direction of the force on the bird. For every action, there's an equal and opposite reaction. Action and reaction force pairs make it possible for birds to fly. Let's skip down here to checking our understanding. If you're driving down the road and a firefly strikes the windshield of a bus, splat, it makes quite an obvious mess in front of the face of the driver. This is a clear case of Newton's third law of motion. The firefly hits the bus, and the bus hits the firefly. Which of the 2 forces is greater? The force on the firefly or the force on the bus? Alright, so let's take a look at the answer. Aha! It was a trick question. Each force is the same size. For every action, there is an equal, remember equal, blah, 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 blah. The fact that the firefly splatters only means that its smaller mass, it's less able to withstand the larger acceleration resulting from the interaction. Besides, fireflies have guts, and bug guts have a tendency to be splatterable. Windshields don't have guts. There you have it. Let's take a look at another example. For years, space travel was believed to be impossible because there was nothing that rockets could push off of in space in order to provide the propulsion necessary to accelerate. On Earth, rockets push off of the air molecules and the ground that they're sitting on. Once you get into space, you don't have that. You don't have any air molecules in space. This inability of a rocket to provide propulsion is because space is, letter A, space is void of air, so the rockets have nothing to push off of. B, gravity is absent in space. C, space is void of air, so there's no air resistance in space. Or D, nonsense. Rockets do accelerate in space and have been able to do so for a long time. What do we think? What do you know about rockets in space? Well, it's a common misconception that rockets are unable to accelerate in space. The fact is that rockets do accelerate. There is indeed nothing for rockets to push off of in space, at least nothing which is external to the rocket, but that's really no problem. Rockets are able to accelerate because they burn fuel and push the exhaust gases in the direction opposite the direction they wish to go. So they don't have to push off of air molecules, just the fact that they expel the exhaust gases out behind them means the Newton's third law is telling them they're going to go forward. And one more. Many people are familiar with the fact that a rifle recoils when it's fired. This recoil is the result of action-reaction force pairs. A gunpowder explosion creates hot gases that expand outward, allowing the rifle to push forward on the bullet. Consistent with Newton's third law of motion, the bullet pushes backwards upon the rifle. The acceleration of the recoiling rifle is A, greater than the acceleration of the bullet, smaller than the acceleration of the bullet, or C, the same size as the acceleration of the bullet. What do you think? Well, the force on the rifle equals the force on the bullet. Yet, acceleration depends on both force and mass. The bullet has a greater acceleration due to the fact that it has a smaller mass. Remember, acceleration and mass are inversely proportional. And number 4, in the top picture below, Kent Budget is pulling upon a rope that is attached to a wall. There's Kent, there's the rope, there's the wall. In the bottom picture, Kent is pulling upon a rope that's attached to an elephant. In each case, the force scale reads 500 newtons. Kent is pulling A, with more force when the rope is attached to the wall, B, with more force when the rope is attached to the elephant, or C, the same force in each case. It says that Kent is pulling with 500 newtons of force in each case, so the same. The rope transmits the force from Kent to the wall or to the elephant, and vice versa. Since the force of Kent pulling on the wall and the wall pulling on Kent are action and reaction pairs, they must have equal magnitudes or equal sizes. Inanimate objects such as walls can push and pull. So, that's a little bit about Newton's third law. Now let's take a look at a matching website that talks about actually identifying those action and reaction force pairs. We know that Newton's third law says that for every action there is an equal and opposite reaction force. Forces always come in pairs, known as action and reaction force pairs. Identifying and describing action and reaction force pairs is a simple matter of identifying the two interacting objects. So we have to identify the two interacting objects and making two statements describing who is pushing on whom and in what direction. For example, consider the interaction between the baseball bat and the ball. The baseball forces the bat to the left. The bat forces the ball to the right. Together, these two forces exerted upon two different objects, the bat and the ball, to form the action and reaction force pair. Note that in the description of the two forces, the nouns in the sentence describing the forces simply switch places. Consider the following three examples. One of the forces in the mutual interaction is described. I want you to describe the other force in the action-reaction pair. Click the view to see the answer. So, in this picture we have a baseball catcher, and it says the baseball pushes the glove left. What's the other part of the action-reaction pair? Well, it must be that the glove pushes the baseball to the right. So if the ball pushes left on the glove pushes right on the ball. How about in this one? In this case, the bowling ball pushes the pin left. If you were listening to the last example, you should know that the pin pushes the bowling ball to the right. And in this one, enclosed air particles push the balloon wall out. That must mean that the balloon wall pushes the enclosed air particles in. So now that we've been able to identify the action and reaction pairs in certain examples, and I've told you all about what Newton's third law says, I'm going to show you some real-life examples. And I want you to identify what is the action, what is the reaction force, and perhaps what is the effect of that action and reaction force pairing. So you get an idea of what I'm asking you to give me when you do the real-life action and reaction force pairs. I'll do the first one with you. As I squeeze the ball, the action force is my fingers pushing down on the ball, and the reaction force is the ball pushing back on my fingers. The effect is that when I let go, the ball springs back to its original shape. So I'm at Memorial Lake and I'm in my kayak. Where do you see the action and reaction pair, and what is the effect of Newton's third law?